and mid-IR. Mid-IR is actually amazing for identifying red supergiants, quantifying their mass loss, distinguishing between red supergiants and AGB stars because the chemistry of their dust is different. But we need a lot more data than we have. We have very limited mid-IR data and mid-IR spectra on red supergiants, and the spectra look mostly like this because we're mainly working from the ground. And it's easy to think that until James Webb comes along, we have no mid-IR spectroscopy capabilities and no mid-IR tools, which is almost true. So I like making a plea for SOFIA, which is a really excellent tool for doing mid-IR work until James Webb comes along. I had a proposal for SOFIA in cycle 7 to start taking mid-IR spectroscopy of red supergiants in the Milky Way with Forecast, which is their both near and slightly farther IR long-slit spectrograph. It's beautiful data. Just from a first glance, we're getting great science on it. It's also so cool because you get to fly on the plane. On the run that I actually did, we flew out of the southern hemisphere and flew down to Antarctica, and you see the southern lights, and the lights are actually so bright that we almost lost pointing, and nobody cared because they just looked so cool. But you also get gorgeous data out of it. Because it's a plane, and because it's a NASA-operated plane, you cannot connect to the Wi-Fi network. You can't even plug a computer into the network without having it virus checked for like a week. So I never got to touch the data while it was being observed. I got to look at it over someone's shoulder as they speed reduced it after we took it. And an immediately noticeable feature was a PAH line at 7.6 microns. You expect to see that in red supergiant spectra, and you don't expect to see it in lower mass dusty stars. So these are big, broad lines. It's possible that that could translate into a photometric signature that distinguishes between red supergiants and even giant contaminants. So it's another great way to use James Webb to actually ID real supergiants and leave out lower mass contaminants. So on that note, I'll leave up sort of summary thoughts from the talk. We know that red supergiants are very important progenitors of things like supernovae and gravitational waves. They're going to be amazing to study with the next generation of observatories. I did not get into the many ways they'll be fascinating with LSST or the ELTs, but they'll be great targets there as well. But there's still a huge amount that we don't know about them. So the more we can learn before these instruments come online, the better we'll be able to immediately take advantage of them. So we can answer a lot of these outstanding questions if we develop good multi-wavelength diagnostics for studying the properties of red supergiants, if we really take advantage of all the observational tools we possibly can, so spectrophotometry, light curves, high-resolution data, ultraviolet and near and mid-IR observations instead of just working in the optical, which many stellar astronomers tend to do. Another thing I didn't get to touch on in detail is coronography of red supergiants. By basically stealing the exoplanet people's coronagraphs, we can get wonderful looks at the circumstellar environments of red supergiants down to very close radii. And we also want to keep improving the models that we have of red supergiant atmospheres, their interiors, their mass loss, how they evolve in binaries with rotation, etc., and in populations, so we can explain what we see. For anybody that has cell phones and still does QR codes, even though they're very 2010, if you want to see some of the papers that I've been talking about, these are some of my students' papers on red supergiants and evolved massive stars. This was the James Webb photometry paper that I did, and this is my red supergiant book, which again is free with an institute subscription. I make no money off of this, I just like telling people about red supergiants. So please access any of these, I can put that back up later. For now, I'll leave the summary up, and I'm happy to take questions. Yes?
Wow. This is fantastic. So one thing that I think is very interesting is, whether or not the giant is filling its Roche lobe, we have winds as we were discussing before, and over a fairly wide range of separations, even before it fills its Roche lobe, or if it never does, it's getting mass through winds. And so if it's the second star to evolve in a binary, or in a triple, if it's the third star to evolve, you're going to have lots of winds captured by compact objects and significant X-ray radiation. In galaxies like 6946, which you showed, these will also be X-ray sources. So my question for you is, some of this X-ray luminosity could be in the range of 10 to the 39 ergs per second or more. How does the star, so now your star, which may not be thinking of the other other star in terms of the amount of mass it's
Yeah.
hitting it, but suddenly it's being irradiated
Yeah.
at a very high rate at X-rays. How does your star respond to that? Does it look different? What's going to happen?
So you'd expect a response for sure. I don't believe that there's much modeling work that's been done at all on what happens if you blast a red supergiant with X-rays. What we have been working on, this was actually Trevor's very first project, is we were trying to find X-ray bright red supergiants. This was the incredibly naive version of try to find red supergiants and X-ray companions. So you take a map of red supergiants, you take the Chandra X-ray point sources, stick them together, and see if anything matches. And it worked great if you found a quasar. So we figured out that something wasn't a red supergiant. But there weren't great instances of coincidence. So this is obviously super limited by the types of X-ray sources that we're looking for, how hard or soft they are, what energy range we're looking over. I think the first step would be to find red supergiants that show some sort of X-ray bright signature and then go from there. So I don't know if that means a dedicated X-ray program or combining it with models to figure out what they should look like, because I've always been very curious about what actual accretion looks like from something as diffuse as a red supergiant onto a companion. I also do like the point that the secondary's evolution is being impacted, because in a red supergiant B star binary, if the B star is massive enough, that's a star that may have one day become a red supergiant and now isn't anymore. So it may not be the primary, but it's still a potential red supergiant that's being affected by non-interacting binary evolution. So I would love to see models that take all these secondaries that in the massive star community we just ignore as like the little things that can take away mass, and see what they do, because it's going to have an effect on them as well.
Thank you.
So in the context of dust production, how much do you think like RSGs could be like major contributors? Because like there's ideas that are supernovae, low-ray stars, and AGB stars, but there's still a problem. Can this help contribute?
So we actually think that red supergiants should be a dominant source of dust production in a young population. So if you have a starburst galaxy or a high redshift galaxy where you really haven't built an AGB population yet, the red supergiants are making all the dust. This was the thing that I had to cut so that I wasn't here for an hour and a half. But we are actually studying red supergiant mass loss. We know shockingly little about how they lose mass and why they lose mass. If you look at probably my textbook, we probably say something like dust-driven, and then leave it alone. In the red supergiant book, it goes into some more detail because they do undergo some dust-driven mass loss, but you need to get dust out of the star first, and it becomes a chicken and egg problem. There could be pulsational processes that lead to dust production. You could actually have some line pressure dust, Alfvén waves. Like there's all these weird mechanisms for how we could potentially produce mass loss and then make dust from red supergiants. And they're very hard to test because it's so hard to look at the dust around them. So this is what we're using the coronagraphs for. And if we can figure out how they make the dust and then the composition of the dust, because we know it's not standard Cardelli dust. It's larger grain, it's grayer, the composition's a little funky. We can hopefully then from there add this as a missing piece to galaxies with dust production that we can't quite explain.
What are the typical mass loss rates during that?
I don't remember. I don't want to guess because I won't remember off the top of my head correctly. But they can be fairly mass losing. The mass loss also isn't always constant. We see red supergiants that are surrounded by sort of shells of dust. And if you remember the picture of VY Canis Majoris, there's structure in the dust. So their rates are decently high, and they can sometimes be extraordinarily high if you have a mass loss episode. I saw another. Yeah. Yep.
You showed how there's variability in different time scales, like in month time scales, and with that you're doing like much shorter cadence. So could you just tell us how those time scales connect?
Yeah, we don't know yet. We don't have nice 2-minute or 30-second cadence light curves of red supergiants. We'd love to get some. That month's time scale is honestly telling us that it can't possibly be the star itself doing something. Something like the Kelvin-Helmholtz time scale just does not match. What we think we're actually seeing is something like episodic mass loss, where the dust is condensing and then cooling and sort of giving us a different impression of what the photosphere is. But we have no idea what the lower cadence timescales are. If you look at long-term light curves of red supergiants, you sometimes see long variability on the order of like hundreds to thousands of days. And that's sometimes attributed to pulsations, although pulsation mechanisms in these also get very bizarre because of the convective regions and how high velocities are in there. So the short answer is all the timescales, and we don't know. But the best studied ones for now are the longer ones, and we're interested in the short mainly because it's a question nobody's asked. They could prove to be terribly dull, but it would be interesting to look and see what's there.
So, thinking about trying to filter out the AGB and RGB stars from
Yeah.
these, are there differences in like the specific chemistry that you would see in one of these stars compared to like a RGB or even AGB star?
So there are. This was actually a possibility that we were playing with when we found our TZO, because we were wondering if it was just a super AGB star. You'll see differences in like the amount of S-process elements that are dragged to the surface. You see different like hot bottom burning products, because you get that in AGB stars and you don't get that in red supergiants. The only problem there is that that means a shell spectra, and I think we got very used to in massive stars working on limited resources because everybody studies the stars second. So it's become, you know, what can we get easily? And if you could get in a shell spectrum of every red star, then we've solved many problems. But if we could do this photometrically, or if we could do this with lower resolution spectra, or something like surface gravity effects. I had a student do a paper where they noticed that the broadness of H-alpha lines, which are there but just tiny in red stars, get broader as you go from dwarfs to supergiants. It's the opposite effect that you'd expect because they're not collisionally broadened. It's an overpopulated metastable state that is easier to overpopulate in a low density atmosphere. So there's tools like that, but something photometric would be way better.
Let's thank Emily. Or one more question?
One more?
One more, yeah.
Yeah.
Okay.
You showed this movie of this kind of pulsating star.
Yeah,
Was that an artist's impression or a real simulation?
that was a real simulation.
Okay, so my question is, where is the nearest red supergiant? And could we actually see this with
Yes.
near infrared interferometry?
Yes. So there's a handful of red supergiants that are nearby. There really aren't many. But you can do this